Hello and most welcome to 1169 of the series. I'm presently filming at Nordre Elv, slightly north of Gothenburg. It's an incredibly lovely day. Here are boats passing. We have all the wonders of the world. And together with the summary in about 50 minutes, 45 minutes I'll guess, I will make a panoramic view, but there is a boat passing right now, so lovely area. György Buzsaki has read about 30 books about time and space. I don't think Julian Barber is included there, for obvious reasons. It's a marginalized book, although when it came, it went actually to the bestseller list, because it's, I would say, rather hard subject to melt. I think it is not the first book one would pick up. If you add György Buzsaki to Julian Barber, you get a fantastic, interesting, I would say, revelation or epiphany, because György Buzsaki is very much to the point. Real genius, no doubt, and he behaves like one, although he has a rather strange accent. I shouldn't be saying anything. But he's definitely in the tradition of James Gibson. He takes William James further. He goes from the stillness of William James that William James inherited from the empiricists, and he brings in movement, which he calls time/space. How far is it can be answered. It is 5 minutes or it's 1 kilometer. Both are valid. Time and space are sometimes the very same thing. It's very hard to have pure space or pure time. Space is needed to make sense of time, and vice versa. And that, of course, is not in the tradition of the empiricists. It's not in the tradition of the idealists. It comes much later. Sorry. So sorry about this cough. Internalization of experience, cognition from action, chapter 5 of the book Inside Outside Mind by György Buzsaki. I move, therefore I am. Haruki Murakami. In the beginning was the act, Goethe's Faust. Not hearing is not as good as hearing. Hearing is not as good as seeing. Seeing is not as good as knowing. Knowing is not as good as acting. True learning continues until it is put into action. Confucius. Theories of cognition have evolved through multiple stages. The first was the outside-in empiricist view, postulating that the brain is an associational, representational device that analyzes the world around us and makes judgments. Then came the Pavlovian reflex theory, which did not make much space for cognition. Everything was a hierarchy of associative reflexes. Similarly, the behaviorist paradigm argued that there is no need to think about cognition, as action can always be explained as a response to immediate external cues. In response to these views, a hard-thinking minority argue that behavior cannot be understood simply as an input-output function, and activity in the hidden layers of the brain is critical. In this chapter, I discuss that internally organized activity in these hidden layers, detached from immediate sensory inputs and motor outputs, is a necessary condition for cognition. Disengagement of the brain from its environment. Humans and likely other animals can imagine into the future and recall the past. We spend a great deal of time on such mental activities. I suggest these activities arise from the brain's ability to break free from external control. The core idea is that cognition depends on prior action-based experiences. Of the world, which allow internally generated sequences to test what-if scenarios and anticipate the possible consequences of alternative actions without actually taking them. This process then helps to select future overt actions. To unpack my hypothesis, consider the three possible brain network scenarios shown in figure 5.1. In a small nervous system, the connections between output and input networks are short and simple. This hypothetical small brain's main goal is to predict the consequences of the animal's actions. Such a brain can make experience-based predictions in a simple environment and at a relatively short time scale. These predictions are generated through learning rules that either apply across generations, evolutionary adaptation, or within the lifetime of the organism. As a result of stored past experience, organisms can deal with the future occurrence of similar situations more effectively. This is the fundamental organizing principle of adaptive systems, of which the brain is a prime example. For example, animals learn to predict the occurrence of food or an unpleasant air puff after some training. More complex brains are organized in multiple loop patterns. These parallel loops, each with increasing levels of complexity of wiring and temporal dynamics, are inserted between the output and input. For example, in mammals, the most direct circuit between senses and muscle activation is the monosynaptic spinal cord brainstem connection. More complex loops connecting these same inputs and outputs include the thalamocortical system and bidirectional communication between the neocortex and several subcortical structures. In addition, a side loop of hippocampal system is dedicated to generate sequential neural activity such that content in the thalamocortical loops is organized into orderly trajectories, allowing simultaneous postdiction, memory, and prediction planning operations. Large and small brains share the same goal: to predict the future. Consequences of their actions. However, the multiple interacting loops and the hippocampal postdiction prediction system allow more sophisticated brains to predict action outcomes more effectively at much longer time scales and in more complex environments. Efficient predictive operations in a complex environment require the storage of vast amount of past experience to compare the current situation to similar occurrences in the past, along with the ability to evaluate and weigh the importance of range of possible actions. Many of these operations require brain computation to continue long after the disappearance of transient sensory inputs and the completion of actions. Such persistent activities are needed to compute the importance of the items perceived and the actions performed. Learning as a result of both phylogenetic and ontogenetic accumulation of experience makes the longer, more complex neural loops smarter or more effective by enabling them to interpolate and extrapolate the events encountered by the organism. Self-organized activity also allows brain networks to disengage from inputs and overt actions. I propose that in a trained brain, communication from the action systems to sensory and higher order areas via the expansion of the corollary discharge circuits allows for such operations. In other words, the corollary discharge mechanism supplemented with a memory loop can substitute for the feedback provided by the body and environment. This virtual action is not translated to muscle movement or heart rate change, yet it is interpreted by the brain as if those actions could have occurred. Such internalized actions, we call them simulations of real actions, allow the brain to inspect its own computations, evaluate internally generated imagined scenarios, and estimate the consequences of potential actions, all without overt inputs or outputs. For a brain network, there is no difference between sensory inputs or activities conveyed by the same upstream neural group in the absence of external inputs. Without external constraints, disengaged processing in the brain can create an internalized virtual world and new knowledge through vicarious or imagined experience, tested against pre-existing and store knowledge. This process, which most scientists and philosophers would call cognition, provides dramatic advantages in predicting the consequence of of actual behavior in complex environments and at long time scales. Of course, the validity of these newly created ideas should be tested eventually in real-world interactions. Until then, the internal content remains a belief. In short, cognition is a time-deferred action. An important aspect of the framework just presented is that most brain structures have two uses. Which I detail in the coming examples. At times, they are connected to sensory input or motor output, directly or indirectly, and vary their cell assembly contents at the pace of changing sensory inputs. At other times, they rely largely on their internal dynamics, often maintained by brain rhythms. I do not claim that processes like input dependence, self-organized activity, and output disengagement develop sequentially or independently. On the contrary, these mechanisms are strongly intertwined, and the degree to which they dominate in each brain depends on the complexity of the circuits, the availability of external cues, and likely other factors. Thus, the emergence of cognition is gradual and quantitative rather than step-like and qualitative. Let me illustrate the emergence of cognition hypothesis by concrete examples. The text will inevitably get a bit technical here and there, but I'll try to keep it simple. I don't think it would be any chance of the latter. I know Buzsaki by now. Even his name is hard to understand. György Buzsaki. Cognition comes from the environment. It is in stark contrast and cannot be understood by argumenting against materialism or contradicting it. It is so different. It is like consciousness stem from matter or objects and their relation. Do you get it? Well, just remember what I said. Cognition stems from matter. It's in a way the same. It goes one step further than James Gibson, I'd say. internalization of head direction sense. The Aristotelian inheritance in cognitive neuroscience is perhaps most evident when people talk about our five senses. The eyes, ears, nose, skin, and tongue contain senses for seeing, hearing, smelling, touching, and tasting. Any sense beyond these classical ones is still referred to as a sixth sense. But there are more, including our senses of temperature, pain, balance, motion, and head direction. Of these, the sense of head direction is perhaps the simplest, as it has only a single dimension, the direction the head points to. Neural substrates of the head direction sense were discovered by James Rank at the State University of New York Downstate in 1984. He observed that neurons in the post-subiculum, a structure that is part of the hippocampal system, fire robustly when the animal's head points in a specific direction, and he called them head direction cells. For example, when the rat faces a corner of the testing box, one set of neurons become active. When the rat turns its head to the right, another set of head direction cells will turn on their activity. For each of the 360 degrees, a different set of neurons fire with equal probability. The head direction system consists of many neurons in a serially connected brain network, including the brainstem, mammillary bodies, antorodorsal thalamic nucleus, post-subiculum, and entorhinal cortex, lateral septum, and parietal cortex, all pertaining to the brain. This widespread representation of head direction in so many brain structures indicates that this sense is of fundamental importance for the brain. Researchers have tacitly assumed that head direction neurons are largely controlled by peripheral inputs, similar to other sensory systems. Indeed, numerous experiments in multiple laboratories show that the head direction neurons are controlled by vestibular, proprioceptive, visual, and ancillary inputs. Such responses, of course, are expected in a sensory system because neurons in all sensory systems respond to the relevant sensory modality. But I often wonder what such sensory neurons do when there is no sensation. If they are active without their dedicated outside inputs, do they show any organized cooperative pattern? To address this question of how head direction neurons work together, we had to wait until the technology matured to allow recording from a sufficiently large population of neurons. We then compare the dynamic interactions in the tiny anterodorsal nucleus of the thalamus during various behaviors. By training an artificial neuron network, we were able to reconstruct the animal's head position from the population interactions of the recorded neurons. When the mouse's head were turning from left to right, this behavior was reliably reflected in a sweep of neural firing sequences as each head direction neuron is tuned to preferred direction. There was excellent agreement between the measured real head direction and the virtual direction reconstructed from the neural firing. The exciting part of the experiment began when the mouse fell asleep, because during sleep all peripheral inputs are either absent or constant. One might expect that head direction neurons will be silent or just fire randomly. Yet, to our surprise, not only did head direction neurons continue to be active, but they replicated the sequential activity patterns seen in the waking mouse. Neurons coding for the nearby orientation continue to fire together, while neurons with opposite head direction tuning remained anti-correlated. During rapid eye movement, called REM sleep, when brain electrophysiology is strikingly similar to its awake state, the neural patterns moved at the same speed as in the waking animal. Recapitulating the activity seen when the mouse moved its head in different directions during waking. In essence, from the temporally shifting activities of cell assemblies, we could determine the mouse's virtual gaze of direction during REM sleep. During non-REM sleep, the activity was still perfectly organized, but now the virtual head direction drifted 10 times faster than it did in waking and in REM sleep. Because no head movement accompanied these changes in the sleeping animal, the temporal organization had to rely on internal mechanisms rather than the external stimuli. The observation that the neural code of the head direction sense is preserved during sleep suggests that the system is maintained by a self-organized mechanism. Of course, this self-organized dynamic is expected to remain active in the waking animal and should contribute to some function. For example, sensory inputs can be combined with the internally generated prediction of head direction to rapidly adapt to reconfigured environments. In case of ambiguous or conflicting signals, self-organized mechanisms may generate the brain's best guess by interpolating across input signals or extrapolating the correct position of the head direction vector from limited or ambiguous sensory information. Overall, these experiments illustrate how internally organized mechanisms can improve the brain's interpretation of the external world. Internal computation continues even without external cues and can perform both interpolation and extrapolation. When I close my eyes, my head direction sense persists, still going up. But the self-organized head direction system needs to be calibrated by active exploration to exploit its potentials. From physical navigation to mental navigation. When you emerge from a subway station in an unfamiliar city with a map in your hands, the first thing you need to do is properly orient the map. North on the map should orient to north in the world. Second, you have to locate yourself. That is, find your subway station. In addition, the vertical and horizontal grid lines on the map can then help you to find museums, your hotel, and other places of significance. Third, you need to distance calibration to determine whether your target is within walking distance of your, or if you would be better off taking a cab. Now you can use the grid to identify any location or the relationship between two arbitrary locations. The alternative to this map-based navigation would require you to memorize a long list of street names. number of steps, turns to be taken, and so on. This latter strategy works well for moving from one place to a few others. However, when the goal is to get from anywhere to anywhere else, maps are superior to route descriptions. To construct a map, someone needs to explore every single locale of the environment. Each location can then be uniquely described by the intersection of horizontal and vertical coordinates on the map. The advantage of this approach is that it allows us to calculate the most efficient route between any two points, thus minimizing distance or time, including potential roadblocks or shortcuts. Physical maps are a prime example of the externalization of brain function. Instead of carefully exploring and memorizing the surroundings in each brain, as other animals must do, humans can navigate effectively and without prior exploration, as long as they can read a map prepared by someone else. Without speech or other direct communications, maps provide clues about landmarks, distances, and specific locations. An entire system in the brain, consisting of several interactive structures, is dedicated to the cognitive map that supports spatial navigation. Head direction neurons provide orientation guidance. The map grid is represented by entorhinal grid cells, and self-localization is assisted by the hippocampal place cells. The source of distance calibration is still debated, but self-motion remains a leading candidate mechanism. The positive impact of practice in navigation on the hippocampal system has been demonstrated by a series of celebrated studies by Eleanor McGuire and colleagues at University College London. These researchers showed, using structural imaging of the brain, that the posterior tail part of the hippocampus in taxi drivers who spent at least 3 years learning their way around London was larger than in matched controls. Thus, taxi drivers' brains grew on the job. This is likely the case whenever navigation skills are increased by practice. Grid maps in the entorhinal cortex Much like the line grid on a physical map, spatial firing patterns of grid cells provide a metric for the neural representation of space. However, instead of the square grid of typical city maps, grid cells tile the two-dimensional surface of the environment in a honeycomb fashion. This pattern becomes apparent to the experimenter when the spikes emitted by a single grid cell are projected onto the floor of the experimental apparatus. Think of a TV screen where a stationary looking picture is formed by the illumination of many points in a fast succession. Compared to the slow temporal resolution of the eye. For grid cells, the moving beam is the rat's movements. To see the hexagonal pattern, we have to wait patiently until the animal passes through each pixel of the environment a few times. When enough spikes are emitted during a long exploration, the hexagonal grid firing patterns becomes clear. Neighboring grid cells have a similar pattern, but with a slight spatial offset. These cells are arranged as semi-independent modules or clusters along the dorsal to ventral axis of the medial entorhinal cortex, where grid scales vary from small to large. This arrangement is like overlaying multiple maps of the same environment with low, intermediate, and high resolution on each other. When the firing patterns of many grid cells are superimposed, they precisely tile the entire floor of the testing apparatus. Their combined activity amounts to a sequence of population vectors or trajectory that describe the animal's position with high precision at any time, because of each position evokes a unique firing pattern among grids of different sizes and locations. This self-independent or so-called allocentric representation describes the relationship of each position to any other position, a map. So, a little summary here. While he's going into the footsteps of James Gibson, there is no doubt there. What he goes is to bring it more into how do we explain this from a neural perspective. And one could say that the revolution of 1887 by Eminem, I like that acronym, is repeated here because we come to understand without an internal representation of space there can be no understanding of external space, so to speak, and also that they cannot be independent. It is ludicrous to state that. Instead, They work in cooperation, which is very, very different from the ordinary take. This is not common sense. Common sense is that the exterior is stable. But the question that arises from György Buzsaki is, how on earth can we understand space? I think we usually say space out there, and we don't ponder any more about it. We don't go any deeper. We just assume it's out there. But that's a big fault. It will make you, as showed in the examples here, not being able to direct yourself in the world. Because if you don't pay any attention to your internal mapping, the external will be affected in every single case. There cannot be any exception to that. You cannot have a transcendental space or a material space, or whatever you call it. You can use it as a tool, but that's a wholly different thing. It's an unusual way of using it, but it's also very different. You can also call this a Wittgensteinian deconstruction of certain concepts, where external space once more becomes real, because in Newtonian space, space is no longer real. It is not cognized, it's not experienced. And of course, that big fault is resolved by quantum mechanics. Quantum mechanics, in a very, very clear way, shows the direction to go. There are always two things. It is the observer and the observed. Take one away and you lose both. Trying forcefully, as most people do today, shove the Newtonian thinking onto yourself will damage you. So clearly shown here, the very brain cells will rupture, they will decay, because if you don't use your internal representation, they don't grow. As in the example of the taxi driver, the enlargement of the brain for location is enormous. You can actually randomly put people into an fMRI and you can directly tell who's a taxi driver in London. It goes all over the world. Those are the most skilled ones. So if you live in a Newtonian world, you will go down the sloppy slope and you will not use your brain, and in the end, my guess would be that you have to rely on habits in some way and other people, and you become, even for your spatial sense, spatiotemporal sense, because they're very connected, you become dependent on society. Once more, as I indicated before, in any organization, societal, environmental, organizational, enterprise, well, enterprise is the word. It is only the one, they are only the one in the top that can make time, that can understand planning. All the other ones just do the calculations, and that those are mechanical, have to be, so they get directed like a director of a concert from above, and we are not aware of that. And there are even people below that think they understand or can direct themselves. That is wrong. If you don't train your locator cells, they will not develop, and in the end you become automatically dependent. It is not a choice. You cannot say I will not be dependent. That choice is not yours to be made. If you don't have the developed brain cells, you will be like an uneducated cab driver in London. You won't find your way. Any arguing, any shouting, any demonstrations, walking with plaques, participating in a political rally, nothing would change that fact. You will be having to rely on others or the organization. External cues is what Buzsaki calls that. And today, as Hari shows, 90-95% don't have access to neither time or space, nor predictive power. They have to make do with the remains, with the shrapnels, with derived things, with copies, could be called models. But the people on the top never ever do that. Not a single case did he find who lives in Newtonian or make up scenery to make plans. It doesn't exist, because that company, that organization would not be permanent. It would be obliterated. I say thank you very much and have a very pleasant afternoon. I will show the surroundings here.